Hello everyone, welcome to my YouTube video. I am Nayana from Sri Venkateshwara College of Engineering. As a part of my final year academic activity, I have been assigned to do a technical seminar on the topic 3D optical storage technology under the guidance of Mrs. Sridevian, Assistant Professor, SVCE. Now, let us see the contents. The contents are Introduction, features of 3D optical data storage, basic components in 3D optical data storage, implementation. Implementation has two processes, 3D optical data storage writing process and 3D optical data storage reading process. We have development of 3D optical data storage issues, conclusions, references. Now, let us see the introduction part. Optical data storage involves storage of data in an optically readable medium such as storage disk, where the device referred to as optically drive uses laser beams to burn bumps of data in writing data on the optically readable medium. The laser beam facilitates the recording of data on a special material on the optically readable medium. Here, the laser beam facilitates the recording of data on a special material on the optically readable medium. Data from this medium is read using a device known as optical drive found in computers. This storage and reading has been through a two-dimensional resolution. Three-dimensional optical data storage, therefore, is any way in which data can be stored and read in a three-dimensional resolution. Now we will see features of three-dimensional optical data storage. Different from 2D data storage, where data is stored on an aluminum film built in a disk and read through focusing of laser beams on its surface. Whereas 3D optical data storage uses nonlinear methods of reading and recording of data. In 3D, data storage and reading are facilitated through the focusing of a laser on the storage medium, where in case the laser passes through other points as it moves in a non-linear way before it reaches the point where data recording or reading is wanted. This is an improvement of 2D optical data storage, where the laser light bypasses every layer of data stored in the storage medium before reaching the desired point, leading to the recording of only 10 layers of data, which is a limitation of current technology. 3D optical data storage uses the methods in which the light interacts with the only address volumetric pixel. In this method, the laser light also passes through the other data points, but due to its non-linearity, it has no effects on them. The 3D optical data storage has the ability to provide the mass storage of up to 1024 TB on a single DVD disk, which is beyond the current 2D optical storage. In this slide, we will see basic components in 3D optical data storage. The process of storing and retrieving data in optical devices requires special devices. The following involves a discussion of some of these components. Firstly, laser, spatial light modulators, we can call it as SLM, lens and mirrors, photorefractive crystals, photopolymers, and then large coupled device, we can call it as CCD. Now we will discuss briefly about all the components. Firstly, laser. Laser is a device used to generate coherent and almost monochromatic radiation, where laser is a light amplification by simulated emission of radiation. The superdirectional electromagnetic radiation is emitted somewhere in the ranges of submillimeter through X-ray and ultraviolet. The fundamental attributes for the laser beam to make them ideal for optical recording are their directionality, coherence, monochromaticity, and brightness. Krypton lasers Argon ion lasers and diode lasers are used to record holograms on crystals. So these are the pictures of the laser. Now we'll see about spatial light modulators, which is also called SLM. During recording, the real image or data is converted to a single beam of light, which intersects with the reference beam. This conversion is done by a spatial light modulator device. The SLM consists of an array of pixels that are usually composed of microscopic shutter that can be controlled by a computer. The LCD displays are also used in place of microscopic shutters. Even SLM pixel corresponds to a bit of data. Therefore, the bits cause a shut or open in microscopic shutters, or go dark or transparent depending on the condition of bit, whether it is 0 or 1. The picture shows the spatial light modulators. This represents the spatial light modulators. This slide is about lens and mirrors. The lenses and mirrors are the major components used to achieve an inverse transform and the Fourier transforms optically. To form the transform, a collimated beam projected on transparency and the transform lens makes the parallel ray bundles make a convergence of the focal plane of the lens. The back focal plane, referred to as the Fourier transform plane, is where the transformation of spatial image is done into a spatial frequency spectrum. The lens carries out at the speed of light a two-dimensional Fourier transform, which leads to the formation of far-field diffraction pattern that can be observed on a screen placed on the transform plane. Here we will see the mirrors and the lenses, where mirrors reflect the light, lenses refract the light. In the next slide, we will see about photorefractive crystals. Photopolymers and photorefractive crystals are the two main materials used in the holographic storage devices. In the coming slide, we will see about the photopolymers. To record data, the photorefractive crystals of materials such as barium titanate or lithium niobate are used due to their optical properties such as high diffraction efficiency and high resolution. Additionally, the materials also show the ability to store permanently till erasure as well as fast erasure through the application of an external stimulus such as ultraviolet light. So, the image here shows how the photorefractive crystals looks. Now we will see about photopolymers. The recent advancement in technology is in the development of photopolymers that can be used as a medium of holographic storages. The photopolymers have less thickness compared to photorefractive crystals, as polymers are usually limited by their optical quality and mechanical stability. Some of the photopolymers used in the market include HRF 150 from DuPont. The imprinting of the pattern in the photopolymer is done by including photochemical changes. So the image shows how the photopolymer looks like. In this slide, we will discuss about charge coupled devices. We can call it as CCD. Charge coupled devices are silicon based devices that contain an array of wells and are created through implants and series of columns. They provide the mechanism to convert optical images to electrical signals. The image here shows how the charge coupled device looks. This is a chip. We can say charge coupled device is a chip, and this is how it looks. In this slide, we will see about implementation. Implementation has two processes. Firstly, we will discuss about 3D optical storage data writing process. For the writing of data to take place in 3D optical storage, a change has to be made on the recording medium, which usually achieved through excitation. The change is usually a photochemical reaction on the medium. In this, several chemical reactions that can effectively work in this new storage have been researched on, and they include photodecomposition, polymerization, photoisomerization, as well as photobleaching. Investigators, however, have mostly focused on photochromic materials which mostly consist of the stilbans, azobans, and spiropans. The writing works on the principle that if the photochemical used is reversible, it is possible to rewrite the data. There are several methods used in recording data on three-dimensional optical data storage, which includes non-resonant multiphoton absorption writing method, sequential multiphoton absorption, microholography writing method, and data recording method. These are the methods which are included in the three-dimensional optical data storage. In this slide, we will discuss about some of the other data writing methods in 3D optical data storage, which includes chromophore pooling method, which involves reorientation of chromophores in the 3D media using laser light, which changes the chromophores to the readable form. Then it's a persistent spectral hole burning, which is also called PSHB method, which uses low temperatures to avoid issues of losing data in the writing processes. The void formation, which involves the introduction of microscopic bubbles into the 3D writing media by use of high intensity laser. Now we will move to the next slide. In this slide, we will see about 3D optical data storage reading process. Several methods have been used in reading data from three-dimensional optical data storage, where most of them depend on the nonlinear nature of light traveling in the 3D writing. Some of these reading methods are optical coherence tomography, which is commonly used in parallel reading 3, two-photon absorption method, the second harmonic generation, which is used mostly in reading information recorded on the pooled polymer materials, use of phase contrast microscope in measuring small differences in between data states in a refractive index. In this slide, we will see about development of 3D optical data storage issues. Despite the major improvements observed with the use of 3D optical data storage and its accommodation to the highly changing technology, there have been hindrances in the development of 3D optical data storage leading to a significantly longer period. Some of the major issues being experienced include media sensitivity, destructive reading, thermodynamic stability. Now we will move to the next slide. Conclusion. Technology has resulted in the use of computers in all areas. Though they provide good data storage, the increased improvements in technology demand for high amount of data storages and that can be easily accessible. Further, the challenges posed by other data storage devices push for a move to other improved and advanced data storages that have high capabilities, high speed, and can accommodate quite large data. These requirements are fulfilled by the use of three-dimensional optical data storage devices. The 3D device can be applied in various fields such as researchers in the space, storage of satellite data, and relatively cheaper compared to current storage devices. As a result, 3D optical data storage is the technology that best fits the future data storage needs. And the coming slide is about the references. These are the references we have gone through. So now we have come to the end of our video. Thank you.